So I'm Michael Kahn from the University of Colorado. I want to thank you for attending today's meeting and for having this kickoff presentation of the Spring 2023 webinar series. The title of my talk is Data Quality and Hidden Influencers in Electronic Medical Records. I've actually decided to reverse the sequence of the topics and start with the hidden influencers topic, because this topic is probably much less familiar to people than is data quality. So we'll start with the second topic first, and then we'll move from there. So first of all, since most of the work that's being done in networks, learning health system networks, have involved electronic health record data, really going to spend the first few parts of the talk looking at examples about why querying data from the electronic medical records is so hard. And on the left-hand side, I have a somewhat tongue-in-cheek, but list of really basic EHR functions that have to be handled by the underlying system. And as you can see, this list can actually go on forever as you bring in more and more features and functions that are part of either a busy office or a part of a busy hospital. So let's step back and sort of say we now want to use that infrastructure, and we want to ask questions from the data that are being collected. And so your task here is you're going to ask a question to your electronic health record analytics team. And sort of the answer that you're going to get to the question that you're going to ask really depends on who you speak to. If you speak to inexperienced analysts, you'll ask 3 of them kind of what the answer is to your question, and you'll easily get 5 different answers, and we'll show why this is the case. If you speak to the experienced analyst, she'll start with, well, what number do you want? And we can work from there. And while, again, this is tongue-in-cheek, this is not too far off from reality. So let's take a look at what's going on underneath the hood. This is where the idea of hidden influencers come in. And we have a whole series of examples that came from real life queries that my team has done over the years. So let's just start with our first example, which is trivial, but this is actually a real example. The details have been changed to protect the innocent, but the framework is exactly the same that we did go through the sequence that I'm about to show you. So the simple question that we're going to use for this first example is, how many patients with diabetes and hypertension did I see last year, 2021? And for this trivial example, we are going to make 2 assumptions, that there are no issues with data quality and there are no issues with defining the diagnoses of diabetes and hypertension. In the real world, these are in fact significant issues. But for this example, we're going to take those off the table and simply look at diabetes and hypertension in 2021. So let's take a look at what this looks like. So here's one way in which this question can be answered. And let me walk you through how to read this diagram. What this diagram is saying that we must have an encounter that includes the diagnosis of diabetes, and also includes the diagnosis of hypertension, and also includes the fact that the provider was me. And this encounter needs to occur during calendar year 2021. And from all of that, we're going to do the number of patients seen in those constraints. That's what NPT at the top means. So this is one way of formulating the answer to this question: how many patients did I see with diabetes and hypertension? It is perhaps the most restricted. It requires the diabetes and the hypertension diagnosis all to occur in the same encounter seen by me during that year. Here's a second way of looking at that question, a little relaxed from the first. And looking at this diagram, what it is saying is that we could have 2 different encounters, wherein one encounter had the diabetes diagnosis, the second encounter had the hypertension diagnosis. Both were encounters in which I saw the patient, both encounters were during the calendar year 2021. We take those two together and we count the number of patients that meet this criteria. Now, the first way of answering the question actually is subsumed by the second way, because it could be that the two encounters are the same encounter. So this is a little more relaxed compared to the first way of answering the question. Well, there is yet another way of thinking about the answer to this question, and that is to say, well, I don't really care who diagnosed the diabetes. I really care that, first of all, I saw the patient sometime during 2021, and that I'm the one that is managing their hypertension. So here, again, patient with diabetes and hypertension had an encounter for diabetes in 2021, not by me, by somebody else, or anybody, could be me, but I was the one who saw them for the hypertension. This would be a valid answer to the question. Obviously, there's the sort of mirror image of that, where in fact, I'm the one who's managing the diabetes, someone else is managing the hypertension, both of us saw the patient in 2021, and we're counting the patients this way. Each one of these is a little more relaxed compared to the previous. And finally, my last variation on the theme before we move on is that, diabetes and hypertension are chronic diseases. Once you're diagnosed with them, they never go away. So maybe the answer to this question could be that whenever they were diagnosed with diabetes and whenever they were diagnosed with hypertension by anybody are fine. And really what I care about is that I saw them in 2021. And maybe I don't even care what diagnosis they had, just as long as I saw them to meet the criteria, did I see in 2021? And this is another way to answer the question. And of course, you can have a really fun time going through all the variations. Here's just a list of 10. I do this when I am trying to avoid doing hard and serious work. I just add a couple more of these variations. I think I'm up to about 25, 26 different variations, all of which are reasonable, rational ways of answering the same request. And the point of this entire sequence is this is why it can drive you crazy in what you're thinking is a very simple question, and yet becomes, because of all of the ways in which it can be structured, it actually becomes a much more complicated conversation than you thought it would be. And my point about hidden influencers, this first point about hidden influencers, is that these structural assumptions are not always obvious to you when you receive the data. And so you may or may not be aware of the kind of structure that was used, or whether or not you agree with the kind of structure that was used in constructing the answer to the question when you get back a simple number or a simple list. So let's continue this conversation and simplify the request. Let's now look for, instead of two diagnoses, let's only look for one diagnosis. And let's take time out of the equation. Let's take the 2021 out of the equation. And there we're looking for congenital anomalies, which once you're born with them, you have them, they never go away, so time does not matter here. I'm using an ICD-9 example. I know we're in the ICD-10 era, doesn't change what the example. So one diagnosis, no time, can't get much simpler than that. Let's take a look at what it took to answer this question. And here is the query that it took to answer that question of one diagnosis with no time. This came out of the Epic electronic health record. Doesn't matter. This is not specific to Epic. All of them have the same issue. And again, this is intended to be mostly the visual impact of the complexity of that request, given how simple it looks on the surface. So let's take a look at what's going on here. So the question is why is this look the way it does for such a simple question? So the issue here is that diagnoses in the electronic medical record, as we've discussed, is being used by many different people to perform many different tasks, and therefore diagnoses appear in the electronic medical record all over the place. And what you're seeing in this query is the fact that the diagnosis that we're looking for might be in the problem list, it might be in the billing record, it might be in clinical encounters, and it might be recorded in the past medical history. And so what you're seeing is this query is probing and looking for that one diagnosis that you asked for in actually 4 different places. It's constructing 4 different ways of looking for the answer to your question. Now let's drill in just a little bit more into the details of just one of these. This is the problem list one. I could have picked the other 3. Doesn't matter. Hidden influencers are also at play here too. So let's blow this up and take a look at what's going on in that particular query. So there's a lot going on in this slide. We'll walk through it slowly. Start at the top. Bottom line is all that you will receive from all of this query is simply 2-column data. You'll receive the internal patient ID and you'll return the patient's medical record. That's all you'll see. You won't see anything else from the list. You will not be cognizant of all of this other stuff that's going on underneath. That is the point of hidden influencers. They influence what you see, but you don't see them explicitly. So let's open up and take a look at what's going on. First of all, to do this query, took the query writer to join together 6 different tables from the Epic database. And what you'll notice if you look a little carefully into the technical details of this 6-table join is that 5 of the tables were joined together using something called an inner join. And the 6th, for some reason that you may or may not understand, the technical people do, was joined using a left outer join. So something clearly is going on with that 6th table that is different from the other 5. Now, there's a lot also going on down below here, where there are a whole bunch of criteria that are being applied here. So let's take a look at these. First of all, there is the diagnosis code of the congenital anomalies code. So that's good. This is where that is the diagnosis that we want is being selected. But we've got this other thing here. It's called problem_status_C, NE, which stands for not equal to 3. So that's doing something. It's pretty cryptic what it's doing. And if you look at it, fortunately, the query writer actually put in what it was that was doing. That is, it's removing, it's ensuring that you're only getting problem lists that were not deleted by the clinician. And then there's this other one happening down here, service_area_ID equals 10. What is that? What's a service area? Why is it there? It's limiting my query. In this case, service area 10 reflects our academic medical center and is selecting patients from that region separate from all of our other regions. And this is, again, is assumption that if not made explicit, you would not know has been used to filter your data. So let's just divert just for a moment. I do know that this network is not creating a common research data model, but I just wanted to show what it looks like, the difference between using a database that is designed to support operational electronic medical record clinical care versus a database that is specifically geared towards research. This same query for the same diagnosis in one of the standard research data models called OMOP. There are many that people use, but this is the one that we happen to use in Colorado the most. That same query would look like this, which is obviously much different than the left-hand side. And the question is, why are these 2 queries looking so incredibly different? Well, a research common data model, a research database, doesn't have to worry about all of the things that an operational electronic medical record needs to look for. It doesn't need to worry about different locations for the diagnosis. It doesn't need to worry about all the historical edits of amendments and deletes and who did them and when were they done and where was it done and all that stuff that's needed for medical legal purposes. And finally, they already have filtered out all of the unwanted patients, whether it's test patients, restricted patients, or anything that has to do with clinical trials. So all this work has been done up front, doesn't need to be done in the query itself. And this is the simplifications that occur from that. Now, what is the influence of the hidden influencers? If that makes any sense. And does it matter? Do these differences, in fact, impact what you find? And this is a study done by Nicole Weisskopf from Oregon Health Sciences. These are her slides, and I thank her for allowing me to use them. And the answer to the question, it really says what you find is really depends, not surprisingly, on where you look. And so what Nicole did here is she was looking at 3 different sources of data. She has the problem list that she's using, chart review, and self-report. This is a little bit different than what we had in our example from Epic, where we were looking at different parts in the electronic medical record. Here, she's looking at different places that are possible both in and outside of the EHR. And she's created Venn diagrams that show the various combinations. There are 7 different combinations that she's showing here about whether or not you found it in one source, maybe you found in the combination of 2 sources, and finally in the center, she found what she was looking for in all 3 sources. And she's interested, Nicole's interested in ECQMs, clinical quality measures, electronic clinical quality measures. And here she has the EQCMs for hypertension, stroke, MI, heart failure, and diabetes. And what you can see here is that the counts and the correlation that she found, depending on which single pair or triplet of sources that she used, sort of varied fairly widely for some things. Diabetes was the most aligned, but you can see in stroke and myocardial infarction and heart failure, there's quite a bit of difference depending on what you find, depending on where you're looking, what you find depending on where you look. Now, this is my last example, and then we'll move on. And first of all, let's take a look now at the emergency department. So this is a picture of what the emergency department looks like to you as a clinician. This is the pediatric analog to the adult ED. And I put these 2 together because what I find most endearing is if you look very carefully at the adult picture, to me, it looks like the patient is flirting with the nurse. But if you look at the pediatric picture, to me, it looks like the nurse is flirting with the patient. Now, from a database perspective, this is what the emergency department looks like, which is pretty complicated. A bunch of tables here that all need to be joined together to get that comprehensive view of the ED. There actually are more tables than this. They actually get involved. But this is what the analyst, when you say, I want some data from the emergency department, you're thinking the pictures, and he or she's thinking this kind of structure. And so here's a query that was done looking at readmissions to the emergency department within 24 hours with an infection. So each one of these boxes represents a table, and each one of those lines represents a way in which those tables are linked together. There are 30 tables here to answer the question of how many patients got readmitted to the emergency department with an infection. So the question to think about is, would 2 analysts who are asked this question do a 30-table query exactly the same way? If you were to ask this question again 6 months from now, would anybody understand what this query was doing 6 months from now? Would even the analyst who constructed this query understand what he or she did 6 months from now? And so these are the challenges that occur with all of the assumptions and trying to make them explicit and bring them to the surface. And these are all hidden from you when you get, again, a number or a patient list. So we're coming to the end of this section. And I guess my request to you is to appreciate that this may be how you come to the table asking with your request, with these sorts of questions, these sorts of assumptions in mind, like I'm using data like from Epic, it's right there, I can see it on the screen. How hard is it going to be to get it out? Can I have it quickly? Gee, I've just changed my mind, I want something else. Oh, I need it by tomorrow. And why that perspective that you might come to the table with is in somewhat conflict with what the data analyst is thinking as he or she is trying to think about how they're going to meet your request. And they've got, a ton of other questions that they're asking, which sometimes drives our requesters crazy. Why are you asking me all these questions? I just want to know the number of asthma patients I saw. Well, this is the reason, and it's trying to nail down these influencers that you may or may not be aware of, making sure that there's an alignment there. And of course, we've got to make sure that we've got the lotto ticket. That's probably top of the list if the analyst is really honest. So I hope what this section has sort of brought forward to you is that these queries that are in English sound to be trivial, really sort of require the nailing down of a lot of assumptions that do not appear in the final work product that you get back, yet they have tremendous impact on differences in the response results that you will get based on how those hidden influencers are in fact resolved. So let's pivot now to the other topic, the data quality. This is perhaps more familiar to most folks. This is actually the shorter section of the talk. One of the issues with data quality is that it's a very broad topic. And it's a little bit like the blind man describing the elephant, where everybody has a slightly different perspective of what it means about measuring data quality. This is a review done many years ago, looking from the information sciences literature, not the medical literature, that looked for what words and what terms are being used to describe data quality. And what you can see here is this substantial long list of words that people feel reflects issues with data quality. We did a survey as part of a study that I'll describe in a second about how data quality is described in the healthcare literature. And what you see here are 10 different publications and their variation in the words in which they used to describe what they felt were the most important features of data quality. And unfortunately here I am personally sort of contributing to somewhat of the diversity and cacophony of this area with my own contribution. And so as the old adage goes, is that when you have so many different ways of describing the same thing, the answer is create the 11th way of doing it that hopefully will be the one way that the one ring that rules them all. And so we actually did that journey a couple of years ago. Took about 2 years. It's about 2 years of herding cats to get everybody together in the same room and really work on trying to get agreement in the community. This was the healthcare community only, with a harmonized framework for trying to put together our different ways of describing and organizing and thinking about data quality so that there could be some way of comparing our different work. This was incredibly tedious work. People have very strong feelings about their frameworks and about their words, and drove me crazy. Don't think I'll ever do this again, but we did accomplish it. And basically what we came out with is a fairly simplified, but what has turned out to be in the test of time, fairly robust terminology for organizing the disparate ways of looking at data quality. It starts with dividing the world into what we call two contexts. And it's really based on whether or not you're only working with your own data, and therefore that's called verification. There, your expectations about what you expect to see are really derived from your own particular data. And then there's a second context called validation, and that's where you're working with either external sources of truth, or you have a gold standard that you could compare, and there your data quality comparisons are based on outside of you benchmarks or comparators. So yeah, verification or validation is the setting in which you're doing data quality. And then we have three major pillars. I won't go into the details. It's in the article. It's an open access article. It is in the reference list. Completeness, which is doing the very basic check of asking the question, are the data even present? No reason to go forward if they're not even there. There's a category called fidelity, which either they may be present, but are they dependable? And then finally, plausibility, which they may be there, but are they believable? And so each of these kind of build on each other. You want to make sure that you have completeness before you really evaluate fidelity, and then fidelity before plausibility. And again, the article sort of goes into this in more detail. Now, this was, again, a very painful process to go through. But what I am pleased to report is that over the years, this framework actually has held up. It has been adopted by the community. And what you see here is a tool developed by the OMOP community. This is the research database community, who has built, this is Claire Blacketier's work on a data quality dashboard. And what you can see is that this dashboard actually expresses that framework. You can see validation and verification and validation as the two major columns in the tool, and then plausibility, conformance, and completeness sitting here across the rows. I would have ordered them in a different sequence, but they're there. And what's also gratifying is that this same framework has been picked up by the All of Us program. PCORNet uses it. Here's the OHDSI. And then the European Eden Network has also picked it up. And others have used the same framework to organize their thinking around data quality. Now let's take a look about the origins of data quality issues. This is basically looking at a life cycle view of data quality, starting at its initial capture at the point of care, its storage in the database, that database managing those data, someone extracting it using much of the tools like we saw in the first part of the talk, doing analytics, and then reporting. And if one just qualitatively takes a look at where data quality issues arise, by far and away, they tend to be up at the entry point, right at the point of initial entry. Although there have been extraction errors, or again, maybe misunderstandings from the issues that we described earlier. Analytic computation, the old phrase, you can lie with statistics and reporting. So let's take a look at sort of that front challenge and looking at data collection in the electronic health record. Well, if one takes a look at how electronic health records are built, they're really optimized to make the data capture as efficient as possible for very busy clinicians whose life is not around entering data, but whose life is around caring patients. So there's a lot of templates and copy and paste that's going on. And there's very little attempt to kind of validate the data, because that would be disruptive to the workflow. And so there's very minimal, maybe min or max limits, possibly drop downs and pick lists and required fields, but that's just about it. So as we take a look, even stuff that you would think would be obvious and simple can have problems. And here, I know there are some people who are listening to this who have heard me speak before. This is an example that I've used for many, many years. I love this example. I just can't let this example go. So please ride with me on doing this again. So let's take a look at the simple stuff. I am a board certified internist, but I work at Children's Hospital. So I work at a facility that I will remind you multiple times, only sees children. So let's take a look at the distribution of the age versus marital status, again, at a facility that only sees children. So here we're going to, this will be the results. We're going to show age down the left-hand column, and then we're going to show marital status for children seen only at a pediatric facility. So here are the data for 423,000 individuals. And just starting right off the bat, what we'll see is that there is a small number of individuals for which we have their marital status 16 years before they were born, 15 years before they were born, and 8 years before they were born. Low numbers, but there they are. Let's just focus on one of the rows, the 6-year-olds here. At a pediatric facility, we have 76 6-year-olds who are married. We have 2 6-year-olds who are divorced, 1 who's legally separated, 3 who have significant others, and 40 6-year-olds for whom, in a pediatric-only facility, we do not know their marital status. Same thing shown in the adult hospital. They have 2 divorced, 3 legally separated, 53 married 6-year-olds. They have 18 with significant others, and I am sad to report they have 1 6-year-old who is widowed. We don't have any widowed 6-year-olds, but they have 1. Let's take a look at a different variable. This is systolic blood pressure. This is, again, Nicole Wyckoff's slide from Oregon Health Sciences. I thank her for allowing me to use that. So this is kind of I call this the porcupine plot of blood pressures by distribution. I'll stop just for a second. I'll pause for a second, make you have you think why this might be happening. So what you're seeing here is, in the era of using manual blood pressure cuffs, people tended to round their readings to the nearest 5. And so every one of those spikes is either a 0 or a 5, because that's where people tended to round that. This is less prominent now that we're using electronic blood pressure cuffs, but that's what's going on here. Now, this is my example that I call human ingenuity knows no boundaries. This is an example, and again, it's going to be difficult to read. It's not important that you look at the details. These are the various values that were seen in a point-of-care pregnancy test result from one of the clinics. This is Marcia Rabel's slide. Marcia Rabel works at Kaiser, Colorado. This is part of the Mini Sentinel work. And she gathered together sort of the results that were coming in for this point-of-care pregnancy test. And under this banner of human ingenuity knows no bounds, what we see is incredible creativity in how to say negative. And so what you'll see here, again, just visually, that there are 28 different ways of saying negative. There are 32 different ways of saying positive. And then, we have some examples like normal. What is a normal pregnancy test? Is a normal pregnancy test that you're pregnant, or is a normal pregnancy test that you're not pregnant? Don't know what that one means. So in data quality, the maxim is that the more you look, the more you find. This is an example from Ritu Kar from the PedsNet network. This is her slide taken from a publication from Injamia. What they show is over time, which is the data cycles down at the bottom, they were putting in more and more checks, looking at more and more details of their data. That's the blue line. And not surprisingly, as they added more checks, the number of issues that they discovered, which is the gray line, increased every time they added more rules with each release of the next data quality checks. But what was most fascinating from the same study, this is the same study, what they looked at is the distributions of things that they found over time. And what you can see here visually is that the red bars progressively go down over time, and they're replaced by the predominance of the blue bars, which dominate towards the end of the sequence. The red bars represent fixable issues. They were technical issues that could be fixed with programming. And the blue bars represent issues that could not be fixed. They were just inherent in the nature of the data. There was nothing that could be done technically. And what you see is the technicians were able to technically fix their technical errors, but that left behind sort of this predominance of unfixable errors. Now, this is a percentage. And so what you see is that the percent distribution was changing. Not surprisingly, missing data by far and away predominates electronic health record data, followed by outliers, just unbelievable numbers that clearly were entry mistakes. And this no matching concepts is a technical issue with the research data network. So again, I mentioned to you that there are now tools out there that one can look at that sort of express data quality checks, such as what was done in BeadsNet. And I come back to the data quality dashboard. This is an open access tool that is available for the OMOP community. And we're going to drill down a little bit about what is happening behind the scenes in this tool. And what Claire has put together is a series of nearly a couple hundred rules of data quality checks that she runs over the data. And as new ones are suggested, she puts them into the library. And what you see here is an output showing the fraction of the rows that violated this particular rule, what the threshold was set by the user of the tool for alerting, and then whether or not it exceeded that threshold. So in the first row, there was a 34% rows violated this rule. Threshold was set to 5%. This rule failed rather. If you go down to the third row, 9% failed with a 10% threshold, and it passed. And so this is a tool where the community can continue to contribute more and more ways of looking at the data and be able to expand the depth in which the data are being explored. And this is just showing you sort of the ability to drill down at any level of specificity based on either the category, whether it's plausibility or completeness or conformance that you're interested in, whether or not you're interested in one of the subcategories. Maybe you only want to look at the failures. In our institution, we run this tool across our OMOP database every single time we develop it. We look at every single failure that occurs. Some failures we accept, and other failures we will pursue. So that ends the data quality perspective. And this is actually my last slide, just coming in almost exactly on the time frame. In terms of thinking about the hidden influencers, I guess my bottom line ask to you is to be kind to your data analysts when they ask you 20 questions to the one question you ask them. What might be simple to you, I hope I've convinced you, isn't simple to them, and that they need to resolve all of these issues, and that you may need to go back to revise the assumptions that you got in a previous query, because these do not show up in the final results, and to be aware that they're there and to be able to have that discussion. And in terms of the second half of the talk on the data quality, it is a large effort. It really is a never-ending effort. So data quality should be viewed as a marathon. It's not a one and done kind of task. And therefore, if you're thinking of establishing a data quality program, please make sure you fund it as a marathon and not a one and done. And finally, the benefit of a strong data quality program, however, is that you have more trust and you have more transparency in the findings that you get from your network. And with that, I'm at the end of my presentation. I thank you for your time and attention. I hope that you found this both entertaining, but also most importantly useful. And we can stop now for questions.